Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Alexandria, in the 2nd century of the Common Era, was a beacon of intellectual ferment, a city where the accumulated wisdom of the Hellenistic world converged with the practical demands of a vast empire. Within this vibrant crucible of learning, Claudius Ptolemy emerged, a figure whose name would echo through centuries of scientific inquiry. His work, spanning astronomy, geography, mathematics, and even optics, offered a systematic, mathematically rigorous approach to understanding the physical world. The prevailing intellectual climate presented astronomers and geographers with profound challenges. The celestial sphere, a source of wonder and a tool for navigation and astrological prediction, remained a complex puzzle. Existing models, while possessing a certain elegance, struggled to account for the observed intricacies of planetary motion. The retrograde movements of planets, their apparent wanderings across the night sky, defied simple, uniform circular paths. Furthermore, the need for accurate celestial predictions was paramount. Mariners relied on the stars for guidance across vast oceans, and rulers and individuals alike sought to understand the influence of celestial bodies on earthly affairs, a practice deeply embedded in the cultural fabric of the time. The Greek astronomical tradition, rich with observational data and sophisticated geometrical reasoning, provided a foundation. Thinkers like Hipparchus had already made significant strides, cataloging stars and developing early models for lunar and solar motion. Babylonian astronomers, with their long traditions of meticulous record-keeping, offered extensive data sets, though their methods were often more arithmetic and less geometrical than their Greek counterparts. Yet, a grand synthesis, a unified framework that could reconcile these diverse traditions and provide a predictive engine for celestial phenomena, was still elusively sought. The instruments available were rudimentary by modern standards. Astrolabes and armillary spheres allowed for angular measurements, but the precision required to fully unravel the cosmos was a constant aspiration. Ptolemy's genius lay in his capacity to absorb, refine, and extend this existing body of knowledge, weaving it into a coherent and remarkably predictive system. He approached these challenges as a profound mathematician and a meticulous cataloger. His work was characterized by an unwavering commitment to empirical data, meticulously gathered and systematically analyzed. He sought to create models that explained the observed phenomena and allowed for precise quantitative prediction. This dedication to mathematical precision, to translating the celestial dance into the language of numbers and geometry, set his work apart. His geographical endeavors also addressed a world yearning for comprehensive mapping and understanding. The vastness of the Roman Empire, its diverse territories and extensive trade routes, demanded an accurate representation of the known world. Existing maps were often fragmented, inconsistent, and lacked a standardized system for measurement and projection. The challenge was to transform a collection of disparate observations and anecdotal accounts into a unified geographical framework, a task requiring both cartographic skill and a deep understanding of geometry and mathematics. Ptolemy's approach was to establish a systematic method for representing the curved surface of the Earth on a flat plane, a fundamental problem in cartography that continues to engage scholars. In essence, Ptolemy provided a comprehensive response to the intellectual and practical imperatives of his era. He offered a universe that, while centered on Earth, was governed by elegant mathematical laws. He presented a world that, while vast and varied, could be systematically charted and understood. His contributions represented a fundamental reordering and refinement of knowledge, providing tools and frameworks that would profoundly shape the course of Western and Islamic science for over 14 centuries. His legacy is that of a builder, a synthesizer, and a quantifier, a scholar who sought to bring order and predictability to the complexities of the cosmos and the terrestrial sphere through the power of mathematics and systematic observation. This pursuit of a unified, predictive understanding of the natural world forms the bedrock upon which subsequent scientific endeavors would build, even as the specific details of his grand designs were eventually refined and superseded. The celestial sphere, a grand dome of stars and wandering lights, presented humanity with a profound intellectual challenge. For millennia, observers meticulously charted the heavens, noting the predictable march of the sun and moon and the more erratic, yet discernible, paths of the planets. The existing models, while offering descriptions, struggled with precision. They could approximate, but they faltered in providing the accurate predictions necessary for navigation, calendrical accuracy, and a deeper understanding of cosmic order. The very fabric of the cosmos, as perceived through the lens of observation, seemed to defy simple, elegant mathematical formulation. The challenge was to forge a system that could describe the observed phenomena and anticipate them with a fidelity that satisfied both the empirical demands of observation and the aesthetic appeal of mathematical harmony. This was the intellectual landscape that Ptolemy navigated, a space ripe for a comprehensive, predictive framework. Ptolemy's response to this challenge was the construction of a geocentric astronomical model, a masterpiece of mathematical ingenuity captured within the pages of his monumental work, The Almagest. This system sought to reconcile the perceived stability of a stationary Earth at the center of the universe with the complex, often retrograde, movements of the planets. The prevailing understanding prior to Ptolemy, largely based on Aristotelian physics and earlier astronomical observations, had established a series of concentric crystalline spheres carrying the celestial bodies. While this provided a conceptual framework, it proved insufficient for detailed prediction. Planetary motions, particularly their apparent loops and variations in speed, demanded a more sophisticated mathematical apparatus. At the heart of Ptolemy's solution lay a series of interconnected geometric devices, each designed to meticulously replicate observed planetary behavior. The primary mechanism was the different, a large circle representing the apparent path of a celestial body around the Earth. However, the simple different alone could not account for the observed complexities. To explain the apparent waxing and waning of planetary brightness and their periods of retrograde motion, Ptolemy introduced the epicycle. This was a smaller circle whose center moved along the circumference of the different. The planet itself then moved along the circumference of this epicycle. By varying the relative sizes of the epicycle and different, and the speeds at which the planet moved on the epicycle and the epicycle's center moved on the different, Ptolemy could generate the observed looping patterns of planetary motion. This concept, while present in earlier Hellenistic astronomy, was developed by Ptolemy with unparalleled mathematical rigor and empirical calibration. The elegance of the epicycle difference system was further enhanced by the introduction of the eccentric. Instead of placing the center of the different precisely at the Earth, Ptolemy offset it. This eccentricity allowed for variations in the apparent speed of the planet as viewed from Earth, a phenomenon already observed. A planet traveling at a constant angular velocity on its different would appear to speed up and slow down from Earth's perspective if the difference center was not coincident with Earth. This subtle shift toward a more realistic representation of observed motion was a crucial refinement. Even with epicycles and eccentrics, a perfect match with meticulous observations remained elusive. The most ingenious and perhaps most controversial element of Ptolemy's system was the equant. The equant was a point on the line passing through the Earth and the center of the different, but distinct from both. The center of the epicycle was conceived to move at a constant angular velocity with respect to the equant, not with respect to the center of the different of the Earth. This seemingly minor adjustment had profound consequences. It allowed Ptolemy to precisely model the observed variations in planetary speed, particularly the fact that planets appeared to move faster when closest to Earth and slower when farther away. The equant provided the mathematical leverage to enforce these observed temporal variations with remarkable accuracy. The construction of these interconnected circles, different, epicycle, and the adjustments provided by the eccentric and the equant was an exercise in applied geometrical speculation. Ptolemy painstakingly calibrated his model using decades, even centuries, of astronomical observations. He analyzed data from Babylonian astronomers, Greek predecessors, and his own meticulous records. For each planet, he determined the precise radii of the difference and epicycles, the offsets of the eccentrics, and the locations of the equants, as well as the specific angular speeds for each component. This process involved solving complex geometric problems and performing intricate calculations, transforming raw observational data into a coherent, predictive mathematical structure. The Almagest, therefore, presented a sophisticated computational engine. For each planet, Ptolemy provided a set of tables derived from his geometric models that allowed astronomers to calculate the position of a planet for any given time. These tables were the culmination of his work, the practical output of his theoretical framework. The predictive power of Ptolemy's system was unprecedented. For centuries, it allowed astronomers to forecast planetary positions with a degree of accuracy that had previously been unattainable. This reliability made the Almagest an indispensable tool for astronomers, astrologers, navigators, and anyone concerned with the celestial movements. The enduring significance of Ptolemy's Almagest lies in the ultimate accuracy of its geocentric framework, which was later superseded by heliocentric models. Instead, its profound impact stems from its systematic approach to scientific modeling. Ptolemy demonstrated the power of mathematics to capture and predict complex natural phenomena. He established a paradigm for astronomical inquiry emphasizing rigorous observation, precise measurement, and the construction of mathematical theories to explain and forecast. The very concept of building a predictive model of a complex system, a practice now fundamental to virtually every scientific discipline, owes a significant debt to Ptolemy's pioneering work. His meticulous attention to detail, his ability to synthesize disparate observations into a unified mathematical structure, and his creation of practical tools for calculation set a standard for scientific endeavor that resonated through the ages. The Almagest was more than a catalog of celestial positions. It was a testament to the power of human intellect to impose mathematical order upon the perceived chaos of the cosmos, a principle that continues to guide scientific exploration. The enduring legacy of Ptolemy's astronomical system, as detailed in the Almagest, rests significantly in the robust mathematical scaffolding he constructed. His meticulous approach to scientific modeling, demonstrating the power of mathematics to capture and predict complex natural phenomena, established a paradigm for astronomical inquiry emphasizing rigorous observation, precise measurement, and the creation of mathematical theories to explain and forecast. The very concept of building a predictive model of a complex system, a practice now fundamental to virtually every scientific discipline, owes a significant debt to Ptolemy's pioneering work. His meticulous attention to detail, his ability to synthesize disparate observations into a unified mathematical structure, and his creation of practical tools for calculation set a standard for scientific endeavor that resonated through the ages. The Almagest was more than a catalog of celestial positions. It was a testament to the power of human intellect to impose mathematical order upon the perceived chaos of the cosmos, a principle that continues to guide scientific exploration. The grand edifice of celestial mechanics described in the Almagest would remain an abstract theoretical construct, incapable of practical application if they were for the foundational mathematical tools that enable the translation of angular observations into tangible spatial relationships. The fundamental challenge for ancient astronomers, including Ptolemy, revolved around the practical conversion of observed angles in the sky to distances on Earth or to distances between celestial bodies. Imagine observing the arc of the sun across the sky or the apparent separation of two stars. These are angular measurements. However, to plot these positions accurately on a model of the cosmos or to understand the physical distances involved, a method was required to relate these angles to linear quantities. This was a problem of immense practical importance. Without a reliable way to bridge the gap between degrees in the sky and units of length or distance, the precise prediction of eclipses, the calculation of planetary positions for astrological purposes, or even the determination of local time would remain rudimentary. The available geometric tools, while sophisticated for their era, demanded a more systematic and comprehensive approach for the complexities of astronomical calculation. Ptolemy's signal contribution in this domain was the systematic development and application of trigonometry. While the foundational concepts of geometry and ratios were well established, Ptolemy elevated these ideas into a practical, computational system. His work laid the groundwork for what we now recognize as trigonometry, focusing on the relationships between the angles and sides of triangles, particularly right-angled triangles. This was a direct response to the pressing need for calculational tools. He understood that the apparent movements of celestial bodies could be modeled using geometric principles, and that the key to unlocking these movements lay in understanding the relationships within triangles formed by lines of sight from Earth to the heavens. Central to this endeavor was Ptolemy's construction of a comprehensive table of chords. A chord, in geometric terms, is a straight line segment connecting 2 points on the circumference of a circle. In the context of Ptolemy's astronomy, the circle represented the celestial sphere, and the chords connected points on this sphere corresponding to the positions of stars or planets. The problem Ptolemy addressed was this: given an angle subtended at the center of a circle by an arc, what is the length of the chord connecting the endpoints of that arc? Conversely, given the length of a chord, what is the angle it subtends? To construct his table, Ptolemy employed a sophisticated understanding of geometry, drawing upon the work of his predecessors like Hipparchus, who had also explored the properties of chords. Ptolemy's innovation lay in the systematic and comprehensive nature of his table and the rigorous methods he used to generate it. He calculated the lengths of chords for every quarter degree of the circle, from 0 degrees to 180 degrees. This level of detail was unprecedented and provided an incredibly powerful computational resource. The table essentially served as an ancient analog to modern trigonometric tables or calculators. Ptolemy employed chord lengths instead of the sine and cosine functions used today. A larger angle generally corresponds to a longer chord, establishing a direct relationship between chord length and angle. Ptolemy's method for calculating these chord lengths was ingenious, utilizing geometric theorems. These included the property that in a circle, the square of the diameter equals the sum of the squares of the sides of an inscribed rectangle, and the theorem concerning chord lengths in relation to inscribed angles. He also applied what is now known as Ptolemy's theorem. This theorem states that for a cyclic quadrilateral, the sum of the products of the lengths of opposite sides equals the product of the lengths of the diagonals. This theorem proved particularly useful for calculating the chord lengths of composite angles. It allowed him to derive the chord for a 1-degree angle by combining known chords for 36-degree and 30-degree angles, for instance, to a process that implicitly involved relationships similar to trigonometric identities. The practical utility of this chord table for astronomical calculations was immense. When astronomers observed the angular separation between two celestial objects, or the angle of a planet's position relative to a reference point, they could consult Ptolemy's table. By finding the angle in the table, they could read off the corresponding chord length. This chord length could then be used in further geometric calculations to determine distances, relative positions, and predict future celestial movements. For example, to calculate the position of a planet at a future date, astronomers would use a series of geometric constructions and numerical calculations, with the chord table providing the essential link between angular measurements and the linear dimensions needed for these computations. This systematic approach to trigonometry, embodied in the chord table, provided a computational framework that was both elegant and remarkably effective for its time. It allowed for a level of precision in astronomical prediction that had not been previously achievable. The table was a finely tuned instrument, a testament to the power of mathematical abstraction to solve real-world problems. It enabled the Almagest to function as a practical guide for astronomers, allowing them to reproduce Ptolemy's calculations and to extend them. The enduring relevance of Ptolemy's work in trigonometry is profound. Modern mathematics has developed more abstract and generalized trigonometric functions like sine, cosine, and tangent. Ptolemy's chord table represents the essential conceptual precursor. His system demonstrated the fundamental principle that relationships between angles and lengths in geometric figures could be tabulated and used for calculation. The very idea of creating a reference resource that translates angular data into calculable lengths is a cornerstone of trigonometry, which continues to be indispensable across a vast spectrum of scientific and engineering disciplines, from the physics of wave motion and signal processing to the engineering of bridges and aircraft, from the surveying of land to the navigation of spacecraft. The principles of trigonometry, first systematically applied and tabulated by Ptolemy, remain fundamental. His chord table, though superseded by more efficient mathematical formalisms, stands as a monument to the human capacity for rigorous mathematical thought and its power to illuminate the workings of the universe. The intellectual landscape of the ancient world, though vast in its philosophical and artistic achievements, often grappled with the practical challenge of comprehensively representing the physical world. The very act of charting the known earth, of transforming terrestrial experience into a structured, navigable format, presented a formidable problem. How could one accurately depict the vast expanse of continents, the winding courses of rivers, and the relative positions of cities and settlements for the purposes of administration, trade, and military strategy? The available data was often anecdotal, inconsistent, and lacking a unifying mathematical framework. Distances were frequently estimated, directions inferred from local knowledge, and the curvature of the earth, while understood by some scholars, was not consistently integrated into practical cartography. This absence of a systematic, mathematically grounded approach meant that maps, when they existed, were often more symbolic or illustrative than geometrically precise representations of reality. Ptolemy, building upon the cartographic traditions of his predecessors, such as Eratosthenes and Marinus of Tyre, confronted this challenge with a systematic and ambitious vision. His treatise, the Geographia, emerged as a comprehensive manual for the art and science of mapmaking. At its core lay a revolutionary idea: the application of mathematical principles to the task of geographical representation. He proposed a global coordinate system, a precursor to our modern latitude and longitude, to assign precise locations to known places. This was a monumental conceptual leap, an endeavor to quantify and systematize the Earth's surface in a way that had previously been unattempted with such rigor. The Geographia provided a detailed methodology for constructing maps. Ptolemy explained the principles of cartographic projections, the mathematical transformations required to represent the curved surface of the Earth on a flat plane. He discussed various projection methods, including an equirectangular projection and, more significantly, his own conical projection, which aimed to preserve distances and shapes more accurately across a wider area. While his projections were limited by the accuracy of the data available to him, they represented a profound engagement with the geometric challenges of mapmaking. He understood that a flat map was an approximation, and he sought to create the best possible approximation through mathematical reasoning. Central to his system was the establishment of a grid of lines of latitude and longitude. Latitude, the angular distance north or south of the equator, was conceptually understood, and Ptolemy utilized existing knowledge of celestial observations to determine these values. Longitude, the angular distance east or west of a prime meridian, presented a greater challenge. Ptolemy established his prime meridian passing through the Canary Islands, a convention that would persist for centuries. The determination of longitude, however, relied heavily on accurate timekeeping, a technology that was then insufficiently advanced. This limitation meant that the longitudinal coordinates in his gazetteer, while systematic, often suffered from significant inaccuracies. Ptolemy's Geographia also contained an extensive gazetteer, a catalog of approximately 8,000 places, each accompanied by its calculated latitude and longitude. This was a remarkable undertaking, a testament to his dedication to compiling and organizing geographical knowledge. He drew upon a vast array of sources, including travel accounts, administrative records, and earlier geographical works, critically evaluating and synthesizing the information to derive coordinate values. The process involved converting reported distances and directions into angular measurements, a task demanding careful attention to the Earth's spherical geometry. Determining accurate distances presented a persistent challenge. Ptolemy, following his predecessors, utilized estimates derived from travel times and reported distances. He endeavored to standardize these by assigning a value to the length of a degree of longitude at the equator, referencing Eratosthenes' calculation of the Earth's circumference. Nevertheless, inconsistencies in reported travel times and the absence of precise surveying tools resulted in distances between places and consequently longitudinal positions frequently being approximations. The Mediterranean Sea, characterized by its well-traveled routes and numerous ports, offered a comparatively better charted region, though discrepancies persisted even there. Despite these constraints, Ptolemy's contribution proved transformative. He had established a framework for conceptualizing geography in mathematical terms, introducing the fundamental concept of a global coordinate system that would support cartography for over a millennium. His Geographia served as the definitive geographical text for European scholars and mapmakers for centuries, influencing the work of individuals such as Toscanelli, Columbus, and Mercator. The very concept of a gridded world map, a systematic spatial representation, owes a profound debt to his methodical approach. The lasting importance of Ptolemy's Geographia resides in its conceptual innovation. He illustrated the efficacy of applying mathematical rigor to the description of the Earth's surface, evolving geography from a descriptive art into a quantitative science. His emphasis on employing coordinates, on striving to measure and represent spatial relationships with precision, established the foundation for all subsequent cartographic efforts. While contemporary cartography employs considerably more advanced projections, satellite data, and precise measurement techniques, the foundational principle of a global, mathematically defined coordinate system, latitude and longitude, is a direct legacy of Ptolemy's pioneering endeavors. His Geographia marks a critical advancement in humanity's continuous pursuit to comprehend and map its own planet, a testament to the enduring strength of systematic inquiry and mathematical reasoning in elucidating the structure of our surrounding world. The lasting importance of Ptolemy's geographia resides in its conceptual innovation. He demonstrated the power of applying mathematical rigor to the description of the Earth's surface, transforming geography from a descriptive art into a quantitative science. His insistence on using coordinates, on attempting to measure and represent spatial relationships with precision, laid the groundwork for all subsequent cartographic endeavors. While modern cartography utilizes far more sophisticated projections, satellite data, precise measurement techniques, the foundational principle of a global, mathematically defined coordinate system, latitude and longitude, is a direct inheritance from Ptolemy's pioneering work. His geographia represents a critical step in humanity's ongoing quest to understand and map its own planet, a testament to the enduring power of systematic inquiry and mathematical reasoning in revealing the structure of the world around us. The ancient world grappled with a fundamental question concerning human perception: how do we see? For centuries, philosophical discourse offered explanations, often rooted in abstract reasoning or teleological arguments. The prevailing theories proposed that vision occurred through some form of emission from the eye itself, an extramission theory, where invisible rays or a visual spirit traveled outward to touch and apprehend objects. This concept, while intuitive in its suggestion of active engagement with the world, lacked a robust empirical foundation. The challenge for any thinker was to move beyond mere speculation and to investigate the physical processes underlying this most vital of human senses, to dissect the interaction of light, object, and observer with a discerning eye for detail and a commitment to measurable phenomena. Claudius Ptolemy, a figure whose intellectual reach spanned astronomy, geography, and mathematics, turned his formidable analytical powers toward the nature of light and vision in his treatise, Optics. This work stands as a profound testament to his dedication to empirical investigation and quantitative analysis, offering a scientific approach to a subject long steeped in philosophical debate. Ptolemy's undertaking was ambitious to unravel the mechanics of vision by studying the behavior of light itself, particularly as it interacted with surfaces through reflection and refraction. His exploration was deliberately experimental, seeking to quantify the relationships between the angles at which light struck a surface and the angles at which it bounced off or bent through a medium. Ptolemy's primary contribution to the understanding of vision lay in his systematic study of reflection and refraction, phenomena central to how light travels and interacts with the physical world. He recognized that vision was inextricably linked to the path light took from objects to our eyes, or, in his favorite extramission model, from our eyes to objects. To investigate this, he employed a series of ingenious experiments. He observed how light behaved when it struck mirrors of various shapes, meticulously documenting the angles involved. His analysis of reflection revealed a consistent principle of the angle of incidence. The angle between the incoming ray of light and the perpendicular line to the reflecting surface was equal to the angle of reflection, the angle between the reflected ray and the perpendicular line. This principle, the law of reflection, was a significant step in quantifying a physical phenomenon, moving the study of light from qualitative description to quantitative law. Even more groundbreaking was Ptolemy's investigation into refraction, the bending of light as it passes from one medium to another, such as from air to water or air to glass. This was a more complex phenomenon to quantify, and Ptolemy dedicated considerable effort to its study. He conducted experiments using spherical vessels filled with water, placing sighting instruments at different angles to observe how the apparent position of objects changed. His objective was to determine the precise relationship between the angle at which a light ray entered a new medium and the angle at which it emerged, bent by the change in medium. While his quantitative measurements were imperfect by modern standards, largely due to limitations in instrumentation and the inherent difficulty of precisely measuring angles in antiquity, his approach was revolutionary. He recognized that a mathematical relationship existed and diligently sought to uncover it. Ptolemy's quantitative findings on refraction, detailed in Optics, indicated that the angle of refraction increased at a greater rate than the angle of incidence, a departure from a common misconception of the time. Instead, he observed that as the angle of incidence increased, the angle of refraction increased at a greater rate, though the relationship was linear. He presented tables of observed angles, essentially providing empirical data that demonstrated this nonlinear relationship. This empirical approach, the systematic collection of data, and the attempt to fit it to a mathematical model, were the hallmark of his scientific method. He was content with stating that light bent. He sought to describe precisely how much it bent under specific conditions. This empirical and mathematical rigor foreshadowed later discoveries, most notably Snell's law, formulated centuries later by Willibrord Snellius. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for any given pair of meteor. Ptolemy's data provided the empirical evidence that such a constant relationship existed. His work demonstrated that the bending of light was a predictable, measurable phenomenon, a crucial insight that paved the way for future optical theories and technologies. His tables, though imperfect, represented a significant attempt to codify the behavior of light, providing a foundation upon which later scientists could build and refine. Ptolemy's extramission theory of vision, while ultimately superseded by the intramission theory, where light travels from objects to the eye, was a product of its time and his intellectual framework. Within this framework, his meticulous study of light's behavior was paramount. He understood that if rays emanated from the eye, their interaction with the external world, including reflection and refraction, was precisely what allowed us to perceive objects. His experiments on reflection and refraction were therefore directly relevant to his theory of vision, aiming to explain how these visual rays traveled and how their paths were altered by surfaces. The quantitative relationships he uncovered provided a physical basis for his understanding of how these extra-emitted rays could interact with objects in a predictable manner. The legacy of Ptolemy's optics resides in the scientific methodology he championed. He approached the study of vision and light with an experimentalist's mind, employing systematic observation and mathematical analysis. This commitment to empirical evidence and quantitative measurement was a powerful assertion of the scientific approach to understanding the natural world. He demonstrated that even complex sensory phenomena could be investigated through careful experimentation and the search for underlying mathematical principles. His work established a precedent for the empirical study of optics, influencing thinkers for centuries and contributing significantly to the development of scientific inquiry. His efforts in quantifying the behavior of light through reflection and refraction, even with the limitations of his era, laid essential groundwork for the eventual development of a more complete understanding of vision and the properties of light itself. The subsequent part will delve into Ptolemy's tetrabiblos and the astrological framework. This part will address the problem of understanding and predicting human affairs and terrestrial events through celestial influences, a significant intellectual pursuit in the ancient world. Ptolemy's unique solution was to systematize astrological beliefs into a coherent, albeit speculative, framework in his tetrabiblos. The focus will be on his attempt to provide a rational, causal explanation for astrological phenomena, drawing connections between celestial configurations and earthly occurrences, and his methodical approach to cataloging and interpreting these relationships. This section will highlight his ambition to apply systematic reasoning to a complex and widely accepted belief system of this time. Modern relevance will be framed by discussing how this work reflects the historical integration of astronomy and astrology, and the enduring human interest in seeking patterns and meaning in the cosmos, while clearly distinguishing this from modern scientific astronomy. Claudius Ptolemy's intellectual endeavors extended beyond the celestial mechanics that map the heavens. They embraced a profound curiosity about the terrestrial realm and the human experience within it. A pervasive concern of the ancient world involved discerning order and predictability in the intricate web of human affairs and earthly events. This quest for understanding, for a framework that could illuminate cause and effect in the lives of individuals and the fortunes of nations, found a powerful, yet speculative, articulation in Ptolemy's tetrabiblos. This monumental work stands as a testament to his ambition to apply systematic reasoning to the domain of astrology, transforming a collection of ancient beliefs into a structured system of knowledge. The tetrabiblos sought to establish a causal link between the observable movements and configurations of celestial bodies and the phenomena observed on Earth. Ptolemy's approach was one of careful compilation. He endeavored to present a rational, almost scientific, explanation for astrological influences. He meticulously cataloged and interpreted the relationships between planetary positions, zodiacal signs, and their purported effects on weather patterns, natural disasters, and, crucially, human temperament and destiny. His method involved identifying consistent correlations, seeking patterns that suggested an underlying, albeit complex, causality. He posited that the celestial sphere, in its grand cosmic dance, exerted a pervasive influence, shaping the fundamental qualities and predispositions of individuals born under specific astrological conditions. Ptolemy's genius, in this context, lay in his systematic cataloging and his methodical approach to interpretation. He sought to refine astrological law, to imbue it with a semblance of logical coherence. He treated astrological principles as a form of natural philosophy, akin to his astronomical inquiries, where observation and the identification of regularities were paramount. For instance, he detailed how the positions of the planets at the time of a person's birth, what is known as the natal chart, could predispose an individual towards certain characteristics, talents, or challenges. He explored the influence of the zodiacal signs, the houses, and the aspects between planets, weaving these elements into a comprehensive interpretive tapestry. The tetrabiblos addressed the problem of understanding human nature and predicting life's vicissitudes by proposing that the cosmos provided a blueprint. Ptolemy's ambition was to decipher this blueprint. He believed that the qualities inherent in celestial bodies, their perceived temperaments, their elemental associations, their positions in the zodiac, possessed active forces that interacted with the terrestrial world. He wrote of Mars as a planet associated with heat and dryness, influencing individuals toward courage and aggression, while Venus was linked to coolness and moisture, fostering love and harmony. These associations were presented as fundamental properties that, when combined in specific celestial arrangements, generated predictable terrestrial outcomes. His systematic methodology involved observing recurring patterns in human lives and correlating them with planetary configurations. While the specific causal mechanisms remained within the philosophical understanding of the era, Ptolemy's insistence on observational evidence and logical inference marked a significant step in the formalization of astrological practice. He aimed to build a system grounded in the perceived regularities of celestial phenomena and their terrestrial manifestations. This dedication to a structured, analytical approach distinguished his work and contributed to its enduring influence. The tetrabiblos also delved into the realm of mundane astrology, the study of events affecting entire communities or nations. Ptolemy examined how the configurations of the fixed stars and planets at the beginning of seasons or the founding of cities could portend significant events, such as wars, famines, or periods of prosperity. He sought to identify celestial indicators for collective destinies, applying the same principles of correlation and interpretation that he used for individual horoscopes. This broader application underscored his belief in a universe where celestial influences permeated all levels of existence, from the individual soul to the fate of empires. The enduring human interest in seeking patterns and meaning in the cosmos is a thread that connects Ptolemy's ancient work to our present day. Modern scientific astronomy has long separated itself from astrological interpretations, while the fundamental human impulse to understand our place in the universe and to find order in apparent chaos remains. Ptolemy's Tetrabiblos serves as a powerful historical artifact, illustrating a time when the study of the heavens was inextricably linked with understanding the human condition. It reflects a worldview where the celestial and terrestrial realms were seen as intimately connected, governed by overarching principles that could be deciphered through careful observation and reasoned analysis. This work highlights the historical integration of astronomy and astrology, a union that persisted for centuries. Ptolemy's contribution was to synthesize these disparate elements into a coherent, comprehensive system, providing a sophisticated intellectual framework for widely held belief. His methodical approach to cataloging celestial influences and their terrestrial correlations, his attempt to establish a causal nexus, and his expansive application of astrological principles to both individual lives and collective destinies showcase a mind deeply engaged with the fundamental questions of existence and predictability. The Tetrabiblos, therefore, offers a profound insight into the intellectual landscape of the ancient world and the enduring human quest for meaning written in the stars, a quest that, in Ptolemy's hands, was pursued with remarkable intellectual rigor and systematic ambition. Claudius Ptolemy's intellectual edifice, meticulously constructed over decades of observation and calculation, represents a profound synthesis of empirical data and mathematical reasoning. His enduring legacy resides in the specific models he proposed for the cosmos or the Earth, and in the very methodology he championed, the systematic application of mathematics to the elucidation of natural phenomena. This rigorous approach, demanding precise measurement and logical deduction, became the bedrock upon which subsequent generations of scholars built their understanding. The Almagest, his monumental treatise on astronomy and the geography, his comprehensive work on cartography, served as foundational texts for an astonishingly long period, shaping the scientific discourse across diverse cultures and eras. For over 14 centuries, the Almagest remained the preeminent authority in astronomical thought. Its influence permeated the intellectual life of the Hellenistic, Roman, Islamic, and Renaissance worlds. Scholars in these traditions inherited Ptolemy's geocentric framework, his complex system of epicycles and deferents designed to account for planetary motion, and his detailed star catalog. While later astronomers would eventually challenge and supersede his geocentric model, the sheer comprehensiveness and mathematical sophistication of the Almagest provided an indispensable starting point. It offered a complete, albeit earth-centered, mathematical description of the heavens, a feat of intellectual engineering that allowed for prediction and further inquiry. The meticulous tables and computational procedures detailed within its pages provided a practical toolkit for astronomers, enabling them to calculate celestial positions with a degree of accuracy previously unattainable. This sustained utility underscores the power of his systematization. Even as the underlying assumptions were questioned, the computational framework itself offered a pathway to refinement. Similarly, Ptolemy's geography established the principles of mathematical cartography for centuries. His work provided a systematic method for projecting the spherical Earth onto a flat surface, introducing concepts like latitude and longitude that remain fundamental to our understanding of spatial positioning. He meticulously compiled geographical data from existing sources, attempting to create a unified and accurate representation of the known world. The geography included detailed maps and instructions for their creation, influencing mapmakers and explorers alike. While his maps were based on imperfect data and contained significant inaccuracies, particularly regarding the size of continents and the extent of oceans, the underlying mathematical framework proved remarkably resilient. It offered a coherent system for organizing and representing geographical information, a critical step in the development of scientific cartography. The very act of attempting to quantify and map the world with such precision, even with the limitations of his era's data, represented a significant advancement in the human endeavor to comprehend and represent our planet. The impact of Ptolemy's work lies in this persistent intellectual continuity. His writings were dynamic frameworks that invited engagement, critique, and refinement. Islamic scholars played a pivotal role in preserving, translating, and expanding upon Ptolemy's astronomical and geographical legacy. Through their own meticulous observations and mathematical innovations, they identified discrepancies in Ptolemy's models and developed more accurate calculations. Figures like al-Batarni refined astronomical tables, and scholars like al-Idrisi created sophisticated world maps that built upon Ptolemy's cartographic principles. This tradition of critical engagement, inherited from Ptolemy's own emphasis on observation and calculation, fueled the scientific advancements that would eventually lead to the Copernican revolution. The eventual shift away from Ptolemy's geocentric model was a testament to the very scientific spirit he embodied. These accumulation of observational data, the persistent need to explain increasingly subtle celestial anomalies, and the development of new mathematical tools eventually revealed the limitations of this system. Copernicus, Kepler, and Galileo, building upon centuries of Ptolemaic astronomy and the critical work of their predecessors, ultimately forged a new heliocentric understanding of the cosmos. Their revolutions represented a progression, a refinement of the scientific project that Ptolemy had so powerfully initiated. The heliocentric model, while different in its fundamental geometry, still relied on the mathematical rigor and observational precision that Ptolemy had so eloquently advocated. Ptolemy's enduring contribution resides in the enduring power of his scientific methodology. He demonstrated that the universe, in its vastness and complexity, could be understood through the systematic application of mathematics and empirical evidence. He moved the study of the cosmos and the earth from the realm of philosophy and speculation into the domain of quantitative analysis. His insistence on verifiable data, on the construction of predictive models, and on the continuous refinement of theories based on observation established a paradigm for scientific inquiry that has persisted through the ages. Claudius Ptolemy stands as a monumental figure who, by demanding that the celestial and terrestrial realms be subject to rigorous mathematical scrutiny, fundamentally advanced the human project of scientific understanding. He provided the tools and the framework for comprehending the world, alongside the intellectual imperative to do so with precision, logic, and an unwavering commitment to the evidence. His legacy is the enduring power of a scientific mind that sought to quantify, to systematize, and to explain, thereby laying the essential groundwork for all the scientific discoveries that would follow. He reminds us that the pursuit of knowledge is a continuous, iterative process, one that thrives on both the brilliance of foundational insights and the courage to build upon and eventually transcend them.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.